All right. So to start off, predict the product of that reaction. If you've got a product, write a balanced equation for it. Like usually I don't write balanced equations. Almost all our reactions are kind of one-to-one. Like how many moles of alkyne react with how many moles of H2?
Yeah, by balanced equation, you just mean like how many moles of this react with how many moles of that.
Yeah, write it like you'd see it in Gen Chem. While you're at it, figure out how many carbons are in that alkyne. I think you guys did pretty well with this on Friday, but it's good to practice it. Pleasure.
Thank you.
I keep drawing heptines. I drew these on Friday. I meant to draw one more. All right, so there's 7 carbons in that. I just want to drive home that these triple bonds are always 2 carbons right there. So your product, if you just have hydrogen gas and palladium, just a transition any of the transition metals, this is one of the reactions that alkynes are going to do, just like alkenes. There's a little bit of a caveat to it. So this will be that. So if we make sure you count your carbons again to make sure you have the right amount. 5, 6, 7. It's easy to get to drawing those zigzags and draw them wrong. And if you were to write a balanced equation, it's that. So the alkyne is going to react with 2 moles of H2 gas. And your 2 moles are going to go to these 2. Yeah, to those 2 positions. All right, so when a question I get asked a lot in these hydrogenation reactions is how many hydrogens do you have? Generally speaking, anytime you use a gas, the gas is going to be used in large excess. It's really hard to control the stoichiometry of a gas. So how do you control the stoichiometry of a solid? Like in the lab, if you were going to, if you knew you needed 12 millimoles of...
You just measure it.
How?
On the scale.
Yeah, you'd weigh it, right? You'd weigh it out on a scale. You'd get a mass for the solid, you know the molecular weight, you divide the mass by the molecular weight, and that tells you how many moles you have. How about a liquid? I mean, measure it as the still.
Yeah.
So you could weigh a liquid, but what else could you do?
Measure it, you graduate some.
Yeah, so you measure a volume, the density, that gives you a weight. You can actually do that with a gas. It's just really hard. The machinery, or the mechanics of measuring how much gas you're adding is really hard. So what you're going to end up with is a volume. You either have a volume of gas at atmospheric pressure or volume at higher pressure, and then how much of that you let through. So it's almost always, certainly any kind of simple reaction, a gas is going to be used just in excess. You're just going to flood the system with gas and react until it's done. And so the reaction of the gas, what controls how much gas is consumed is just the other reagents. So you're never going to see H2 be the limiting reagent. All right, so I can't recall if I went over these or not. I wanted to emphasize it a little slower. If we take this same compound and we use a catalyst, and again, so Lindlar's catalyst is the word I'd like you to know. Lindlar, the name. This has got palladium in it.
Doesn't the book also call them like poisonous?
Yeah, well, poisoned, right? The catalyst is poisoned in that it's just not as good a catalyst. And it actually gets really complex. And the way Lindlar figured this out was not any kind of rational science. I'm not taking anything away from him. But he basically just started with a palladium catalyst and just started adding crap to it until he found a system that would only react with alkynes. This is not a bad way to do science, right? A lot of people, well, the story we all tell about science is you have this hypothesis based on all these theories, and then you test the hypothesis. And then when chemists go, so every year there's actually there's a bunch of chemistry conferences. There haven't been in the last year, but you understand. But usually we go and we have these conferences and we all tell each other about our work. And the story is always like, well, I had this great idea and it just worked perfectly. We always tell it that way. Usually there's a lot of fits and starts. The worse your theory is, the worse your actual understanding is, the more it pays to just sort of randomly try everything. Right? If you have no idea of what's actually happening in the flask, just dump stuff in. That's easy to tell. If you know the result you want. And so what Lindlar wanted, he wanted this reaction to just reduce the alkyne to an alkene and stop. Right? And so that's an easy thing to test for. He starts with his catalyst, starts with his alkyne, pumps some hydrogen in there, and his reaction stops with an alkene. When he finds a mixture that does, bang, publish it, patent it, it works. All right, so I want you guys to you can know the phrase poisoned if you want. The other stuff in here basically makes the palladium not as good a catalyst. So it reacts with the alkyne, it doesn't react with the alkene. Lindlar's catalyst will only reduce alkynes. Right, so if we started with a molecule that had a couple of double bonds in it and an alkyne, right? If we do Lindlar's catalyst, nothing's going to happen to the alkenes. The alkyne is reduced to an alkene, and that alkene is always going to have the 2 H's be cis because the hydrogens have to do a syn addition. Right? If we took this same diene alkyne, treated it with just hydrogen and palladium, right, again, the H2 is going to be there in excess. It'll reduce both alkenes all the way. It'll reduce the alkyne all the way. So the product here would be 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Right? So basically, all the alkenes, all the alkynes, if you do hydrogen and palladium, get reduced all the way down to the alkane. I talked last time in class on Friday that benzenes don't do this. So if we throw up right, so if I take benzene, I've got an alkyne in there, I've got an alkene in there. I'll reduce the alkyne, I'll reduce the alkene, I won't do anything to the benzene. 1, 2, 3, 4, 5. All right, so basically chapter 8 and chapter 9, benzene doesn't do any of that chemistry. If you see a benzene ring, a 6-membered ring with 3 double bonds, just leave that alone. It's only chapter 8 and 9. I've said this a bunch, I think. Orgo 2, you might even start with this. I don't know where Amanda will want to start, but benzenes definitely do chemistry. They do some really cool chemistry, but they don't do it in this class. Question?
Can you go over why Lindlar's catalyst results in the cis addition?
It's just not as good a catalyst. There's a whole bunch of other stuff added to it. You guys aren't going to have to draw a mechanism or explain anything.
Any of these?
It's basically a memorization that if you have this poison catalyst,
It slows it.
it's not even that it slows it down. The catalyst actually doesn't interact with an alkene.
Okay.
All right, so the hydrogen loads onto the Lindlar's catalyst just like it does palladium or rhodium or any of those. But then the alkene can't interact with that catalyst. So it only works with the alkyne.
And the product will always be cis, right?
Product is always cis with Lindlar's catalyst. There is this other, let's go back to our more simple, and I'm not going to, you don't have to know the mechanism of this one either. So if you treat an alkyne with sodium metal and ammonia, you get a reduction to the trans alkene. Right, so like I said, this goes through radicals. It's actually a really complex mechanism. If you're enjoying mechanisms in this class, chapter 9 has it's like a whole page. And it's a beautiful reaction to run. If you dissolve sodium and ammonia, you get this really lovely blue color. A much deeper blue. So ozonolysis is basically Duke blue, and dissolving metals kind of Carolina blue, if you're from around this area. Really pretty color. But that reduces it to the trans alkene. So again, if we came over here, started with this diene alkyne. All right, if I treat this thing with sodium and ammonia, that's just a 0 there saying that that's sodium metal. Nothing happens to the alkenes. The alkyne becomes a trans alkene. Yeah.
So on the PowerPoints, you said that the first reaction is concerted without Lindlar's or the sodium metal or ammonia. So it's just all of that is happening in one step. The first one, like both.
Here? No. Okay, so that's a good point. Sorry. It's a very perceptive question. So the first addition of hydrogen does give us, all right, so this is H2 and palladium, right? You get the cis alkene. So 2 H's add in a concerted fashion. Syn. You get the alkene. But then this alkene, right? If I drew this alkene and said reduce it or react it with hydrogen and palladium, it would reduce. So let's go there. So molecules don't know. Another question I get asked a lot is how do you know when the reaction's done? And the way you know the reaction's done is you look at all the molecules you have and they won't react with each other. Right? Molecules don't know where they started. So that alkene I've drawn in brackets, it doesn't know if it's a starting material or an intermediate. It's just an alkene, and if there are reagents around with which it will react, it reacts. So yeah, it's a concerted process, but those 2 steps aren't concerted. All right, so that's the reaction. That's how we reduce alkenes. I talked on Friday about alkylating alkynes. So basically, the reactions in chapter 9 go like the reactions in chapter 8. All right, so this hydrogen in palladium or hydrogen in any transition metal, alkyne goes all the way to the alkane. Lindlar's catalyst poisons that, you stop at the cis alkene. Sodium and ammonia, you stop at the trans. There's others then that go just like you'd expect. Right, if we add HBr to this thing, if we had one equivalent, actually we'd get a mess here. Let me let's just stop like that. Right, so if we take the alkyne and HBr, we can add one HBr. Br is an electron withdrawing group because it's electronegative. That makes this alkene a little less nucleophilic than the alkyne. If we put in another HBr, we get 2 additions. The bromines go on the same carbons. You can do this with Br2 as well. It gets pretty complex. You get both cis and trans for reasons that aren't real well understood. And if you add a second equivalent, Br2, you get 4 Brs on there. This isn't a terribly useful reaction. People don't do this a lot. There aren't many products you're going to find that have 4 bromines on 2 carbons next to each other like that. So there's not really a reason to make those. Ozonolysis. So if we do an ozonolysis, give you a different. Let's take this alkyne and ozonize it. And here we don't really have to do any kind of reduction like we do with an alkene. In an alkene, we use either a sulfide or zinc to reduce that. This just sort of, all the oxygen gets incorporated. Again, the benzene won't react, but we get carboxylic acids. So the ozone cuts through all 3 of the carbon-carbon bonds in that alkyne, and you end up with adding 3 oxygens now, right? So if I cut through all 3 of those bonds, the carbon needs 3 more bonds. It makes them all to the ozone. So you get this butyric acid, and then you get benzoic acid. But again, that basically is, it looks a lot like, when I tell you guys that if you know the chapter 8 reactions, you pretty much know the chapter 9 reactions, I'm not suggesting there aren't some modifications to the chapter 9 reactions, but you have a good place to start in there.
For the middle reaction there, sorry, where you add the 4 bromines, is the only reason you draw 2 of the alkene because you have Br2, right? Or
well, because you have cis and trans, right? So if this went exactly like the alkene, you'd get anti-addition. You'd only see the trans. And that usually is the major product. But there's a lot that depends on, like the stereoselectivity of this reaction depends on temperature and solvent and concentrations, what the substituents are. So it's not as straightforward a reaction as it is with the alkene.
yeah, I thought the 2 were being added together to create the 4 bromines.
No. You get, right, this would be, if we use one equivalent here, that's our product. We get a mixture of those 2 alkenes. But if we add excess bromine, both of these will give the same product. If I add Br2 to either the trans or the cis alkene, I get the same product. And that reaction basically goes like the halogenation with alkenes, that you can't do it with iodine. Faster with chlorine, but it's harder to stop at one. Like I said, I probably shouldn't say this in class just in case I can't imagine I'll ask you that question. Right? It's not a real useful reaction. It's fairly complex. Even the one above that, the top reaction, the reaction of HX with an alkyne, that looks like it ought to just be exactly like the reaction with an alkene. Turns out if you go into that and look at the kinetics of that reaction, HX appears twice in the rate line. So if I double the concentration of HBr, the reaction actually goes 4 times as fast. And the reason for that, I mean, it's complex. The alkynes aren't quite as nucleophilic as the alkenes, which we'll see in the next example. Ellie, you had a question?
I did. If you give us a reaction like this and you ask for the product, should we assume that it goes to the completion in the alkane, or should we assume that it goes to the alkene?
So both of the top two here, if I don't give you stoichiometry, so the way I do it, if stoichiometry is important, and both of those reactions, if you use one equivalent of HBr, you get the alkene. If you use excess, you get the alkane. If I don't tell you stoichiometry, to me you can draw either one, right? So if I just say HBr, you're totally fine telling me it's the vinyl bromide. Or you're just as fine telling me it adds twice. If I tell you though, one equivalent, you got to draw the alkene. If I tell you excess or 2 equivalents, you got to draw the alkane. Make sense? Yeah. All right. Okay, so this all brings us to the addition of water to an alkyne. Either Markovnikov or anti-Markovnikov. And they both produce something called an enol, which is probably the most interesting thing that happens with these additions. So I'll say to an alkyne. All right, so let's take our phenylacetylene. I need to write that more clearly. So, like I said, it turns out that alkynes are not as nucleophilic as alkenes, all else being equal. And to hydrate an alkyne, you really need some mercury in there. Or, like I said when we did oxymercuration, you need some Lewis acid in there. Today we tend to use gold 1. You can catalyze this reaction with a variety of transition metals, but you need something stronger than just H3O+. And here is the product. So like I said, these reactions tend to go just like chapter 8, but that doesn't look anything like a product you'd get in chapter 8 by addition of water. Right? And if we actually keep track of what's added there, so like I said, we're going to add H2O, right? And we have, but they've not gone where you'd expect them to go. So the mechanism starts out very much like, okay, so I'm also going to ignore the mercury here. I'm going to draw this mechanism as if the mercury's not doing anything. If you look at the textbook, if you look at the PowerPoint, the mercury is definitely doing something and you need it in there. But I'm just going to draw this with the alkene attacking the H3O+. And here's really why you need that alkene. So one of our hydrogens is coming here. We add the hydrogen, we get the more stable vinyl cation. It's secondary, it's benzylic, but here's the thing, it's a cation on an sp2, it's an sp cation, which makes it quite unstable. And this is why we need the mercury. This cation, formation of this cation is pretty slow. All right, and then we have water, which will attack and I really can't emphasize this enough because I saw it a lot on the quiz. I'm about halfway through grading, the assignment you guys turned in this morning. All right, so the attack is from water. Both of the hydrogens come along with it. So we've now added H3O+. Right? So the thing is, water attacks the cation. Both hydrogens come with it. This oxygen winds up positive. You need two steps here. Still saw a lot of people adding water would add to a cation and you just have OH show up. All right, so both hydrogens come along for the ride here. And then you've got water in there. Water will take one of these protons. Hey, look at that. I totally blew away my alkene. All right, sorry. Back up. Draw my intermediate here. I got rid of the alkene. This intermediate with the OH2 on it needs to have a carbon-carbon double bond there. I did not mean to eliminate that. All right. So now, this looks like what you would predict. If I had put this up here, and said, if I put the reaction up and said draw the product, you guys hopefully would have drawn something like that. H and OH add across the pi bond. OH on the more substituted carbon, H on the less substituted carbon. Less one. All right, so Markovnikov addition of water across that alkyne. All right.
Should we know the mechanism for this?
Not so far. The question at home, if you just heard that, was should you know the mechanism? Thanks for asking that. In the book, all right, the initial attack of the alkyne goes to the mercury. It's catalytic in mercury. Mercury adds, then it gets kicked off. Excuse me. It complicates it, so you don't need to know the mechanism up to here. This is called an enol, right? So there's an alkene and an alcohol, and this shortens down to enol. The enol will turn into a ketone or a carbonyl. And they all do. Every carbonyl compound that has a hydrogen on the atom bonded to it exists in equilibrium with an enol. Most of the time, the carbonyl, the CO double bond, is more favorable. I'm going to take you to the carbonyl, the mechanism to the carbonyl. So from the enol to that carbonyl, you should know that mechanism. Yeah.
And so throughout this mechanism,